5 papers during these last few months in connection with this topic. Thank you very much. Yeah. Yeah. Jump forward. I mean, yeah, but, maybe even told you. Yeah, but yeah. I mean, he has written, me as well, but so the fact that I did not have time to emphasize here, and what in some sense, and even I had no time to tell to Alessandra, but the fact is that the algebraic geometry and Döhling's theorem was not used directly, but Bombieri and Birch. He wrote in the same letter that he thinks actually Bombieri should say that this, how to say, this work is correct because of the links, and this is a, but what, so that means this result of the link was worked into a result, was transformed into a result of closed Riemann sums in an appendix of Bombieri and Birch to the mentioned paper of Friedlander and Ivanis in 85. So that means already 28 years ago, Bombieri and Birch did this job, what was the concern of
the estimate for closed Riemann sum is doesn't need the link, or does it?
So that no, it needs. But this was not done by Jung, but by Bombieri and Birch, and published 28 years ago. Pardon? Yeah. But so because of this reason, it was not really necessary.
To teach, to give a course on bounded gaps, it wouldn't be complete without this algebraic.
I mean, completely, unless you just quote the result. Yeah. So it's a part. Yes, it's a part of it. Yeah, that's true. Yeah, thank you. Yes.
Could you please take your seats for the next lecture? Okay. I'm Janusz Makowski from the Technion in Haifa. I'm very honored to be able to chair the last plenary lecture. Our speaker is Péter Komjáth, who was a student of András Hajnal. He was elected 3 years ago to the Academy, and he is currently chairman of the computer science department at ELTE. And he is a specialist in infinite combinatorics, in spite of the word finite in the title there, which is very unusual in his case. Please.
Thank you. First, let me thank the organizers for inviting me to this conference, which is obviously one of the best conferences in recent times. There's no surprise that this lecture is dedicated to, and we'll speak mostly about the theorems and conjectures of Paul Erdős, PGOM, LD-AD-CD. Now, probably almost everybody, or maybe everybody knows, but let me just mention the definition of a graph, which is simply a pair of two sets. One is the set of vertices, an arbitrary set, and the other is any subset of the all two-element subsets of V. So certain points are joined, certain are not. We simply do the usual definition. This is important because we will speak about infinite graphs, and then you have to know exactly what you mean under a graph. And here is an equally short introduction to set theory. Well, in set theory, we work with infinite or even uncountable sets, and the sizes, the cardinalities of the infinite sets are enumerated in a certain list, which starts with Aleph naught, Aleph 1, Aleph 2. Aleph naught is simply the cardinality of the set of natural numbers, a countable infinite set. Everybody is familiar with that. And there is an immediately succeeding cardinal, Aleph 1, so that's the next cardinal. In other words, the least uncountable, the smallest uncountable sets have cardinality Aleph 1, and there is a further next cardinal, Aleph 2, which is immediately following Aleph 1, etc., etc. So if we want to prove something, the first case usually in a set theory problem is Aleph 1. If I want to meet the first interesting case or the first case ever, then we try to prove it in Aleph 1. Let me point out that one of these Alephs is C, the continuum. We just don't know which. But if we assume the continuum hypothesis, it is Aleph 1. Now, there was a great lecture on Erdős's work in combinatorics, or actually random graphs, one of his favorite topics. And there was another great lecture on Erdős's theorems and conjectures in number theory, which is known to be another of his favorite topics. But there was a third topic which Erdős liked very much, and that is set theory, which is much lesser known. When Erdős was young, he did a lot of work in set theory. He proved very clever theorems, which by that time were quite complicated, were considered quite complicated. And he had some kind of a youthful enthusiasm toward set theory, which is reflected in how he closed some of his letters in the 40s. He wrote, let C be with you. C is contour. And then suddenly something happened. What happened was that forcing was born almost exactly 50 years ago. Forcing is that great method by which set theory was totally transformed into a different science, essentially. Forcing is the method by which we can prove that certain statements in set theory cannot be proved. Essentially, states that if we have a model of set theory, then with some methods we can extend to a model where a certain statement does not hold or holds. So the first example, and a very good example, is the question of the continuum hypothesis. With forcing, any model of set theory can be extended to a model where the continuum hypothesis holds, and with a different kind of forcing, it can be extended to a model where the continuum hypothesis fails. And if there is no model of set theory, then set theory is contradictory, and we are damned anyway. This totally changed set theory, so there are literally thousands of theorems saying that this natural question of sets or groups or topological spaces, whatever, has the following answer. In this model, it is true. In this model, it is false. And now, Herder didn't like this change. And his usual reaction was this sentence to results of that type. And I think that what he really believed is that there must be one universe of set theory when everything is either true or false. We only have to learn which one. And we may find perhaps better axioms. So that's okay if we change our axiom system to something better by understanding nature better, but it is not the way that everything is true in some universe of the universe of set theory, and it can be differently in a different universe of that. This is not shared by most of the researchers in the current set theory, but there are some directions which are closer to Erdős's view. So there is a theory which can be interpreted that set theory has a unique axiom system where everything is decided in some way. And also I once read a top set theorist writing that we use forcing to find out what the right sentences are, right sentences which can be decided in ZFC, i.e. without forcing, and then we prove them. So forcing is just a tool of finding what we really have to prove. Now we start with a finite theorem, which was already mentioned in some lectures. This is a theorem of Bill Tutte, which says that for every finite n, there is a triangle-free n-chromatic graph which is finite, of course. This can easily be proved. There are, in fact, many different proofs for this. And for the sake of probably just a few people, maybe for nobody, who doesn't know what the chromatic number of a graph is. Here's the definition. The chromatic number of a graph, finite case, is the number of colors needed for a good coloring of the graph, which means that we color the vertices, and we require that if two vertices are joined by an edge, then they get different colors. As it is quite well known, Erdős tried to generalize essentially every finite combinatorial expression to the infinite. He tried to see if there is an interesting or meaningful counterpart in the infinite case. I think with Ulam they said that the infinite we do right away, the finite takes a little longer, which already reflected something which is true, that in many cases the infinite version is much simpler, even trivial, of some deep finite problems. However, Erdős was quite clever, and he knew that may occur because we just don't formulate the right form. So you have to find the right form of the question to make the problem interesting in the infinite, or even hard. Of course, that was easy for him to find the good conjectures. So what happens if we ask that question for infinite cardinals? Now, first of all, there remains the question, what is the chromatic number for infinite graphs? The definition of a chromatic number is exactly the same. The least number of colors needed for coloring the vertices of the graph, so that if two vertices are joined by an edge, that they get different colors. Notice that there is something hidden in this definition, namely that there must always be a least number of, among the cardinals which occur as the cardinality of colors under this coloring. So we use in this definition, or we presuppose in this definition, that if we have some collection of cardinals, then there is always a least among them, which requires the axiom of choice, that the cardinals are well ordered. And in fact, I cannot resist mentioning this theorem. With Fred Galvin, we proved that the axiom of choice is indeed equivalent to the statement that every graph, finite or infinite, possesses a chromatic number, where the definition is exactly that. Another well-known and indeed very nice theorem on infinite graphs is the Erdős-de Bruijn theorem, which says that if n is a natural number, then an infinite graph has chromatic number at most n, if and only if the same thing holds for all finite subgraphs, i.e. every finite subgraph has chromatic number at most n. Obviously, one direction is trivial. If the large graph has chromatic number at most n, then so has the smallest one. The other direction is the whole thing. And this is very popular among finite combinatorialists. And the nice thing about it, that there are many different proofs for it. So you can choose your favorite one. You can prove it using Zorn's lemma. You can prove it by transfinite recursive argument. You can use ultrafilters, if you like. Erdős and de Bruijn used Tichonov's compactness theorem on topological spaces. But of course, this is really simplest proof is saying that this is really a special case of Gödel's compactness theorem, which is something that no finite combinatorialist would like to hear. Now, this effectively kills the theory of infinite graphs with finite chromatic number. There are no such graphs. There is no such theory, because the only reason that an infinite graph have a chromatic number, I don't know, 27, is that there is a finite part of which makes it chromatic number 27 at least, and then we are done. Now, to returning to the original question, Erdős and Rado indeed proved the infinite counterpart of Tutte's theorem. For every infinite cardinality, kappa, there is a triangle-free graph with chromatic number greater than kappa, and originally the cardinality of that example was 2 to the kappa, and then they changed it to kappa plus, which is the optimal cardinality. Kappa plus is the cardinality following immediately after kappa, so the least cardinal, which is bigger than kappa. Now, of course, there now here is another theorem, very famous and frequently mentioned, even several times mentioned at this conference, of Erdős. If n and k are two natural numbers, then there is a finite graph, x, whose chromatic number is greater than n, and it not only omits triangles, but it omits all circuits of length up to and including k. So it omits triangles, it omits circuits of length 4, 5, ... etc. Okay. This is an important theorem in finite combinatorics, first because of his original proof method, and of course the corollaries. And now there's just one problem with this theorem, that it speaks about finite things. So one can ask, can we generalize these two infinite graphs? We could generalize the original Tutte theorem to infinite graphs, verbatim. Can we literally generalize this to infinite graphs? And Erdős tried that for long years, and he could not. And it was quite a surprise that the reason that he could not prove the natural generalization was that it was not true. If we have a graph which does not contain a fourth circuit, then its chromatic number is at most countable. It can be colored by countably many colors. It's quite interesting to see how surprised Erdős was, which can be read from some of his problem papers concerning these topics. Now, after this, it was very easy to find the right generalization of the Erdős theorem to the infinite, which was done by Erdős and HUN-REN, which essentially says that it is not the girth which we can increase, but the odd girth. We can omit all odd circuits up to a certain length. If we are given an infinite cardinal kappa and a natural number n, then there is a graph of chromatic number greater than kappa, which omits all odd circuits up to length 2n plus 1. Of course, it's impossible to omit all odd circuits of any length, because that gives a bipartite graph. And with that, two results, we can exactly tell what are the graphs which appear in every uncountable chromatic graph, which are obligatory for being uncountable chromatic. These are exactly the bipartite graphs. Every finite bipartite graph must appear, and we can omit any finite graph which is not bipartite. The second statement being simply that a finite non-bipartite graph contains some odd circuit, and then we just apply the previous theorem with long enough, omitting long enough, sufficiently long odd circuits. Now, another interesting remark was that exactly the same holds for replacing uncountably chromatic by the chromatic number being larger than kappa. So it seems that in this theorem, or problems like this, uncountable chromatic and chromatic number being larger than kappa are the same. So somehow there is no way of distinguishing uncountable chromatic number, uncountable cardinals as chromatic numbers. Another very important thing which Erdős and Hajnal did was a definition. So sometimes definitions are almost more important than theorems, and this was a very interesting and useful definition, the definition of another invariant of graphs, the coloring number. The coloring number of a graph X is the least cardinality, finite or infinite, mu, such that the following is true. V has a well-ordering so that every vertex is joined into less than mu smaller vertices. This definition sort of came out of the proof of the previous theorem, and this can be regarded as the greedy version of the chromatic number. Why? Because if we have a graph whose coloring number is, say, Aleph naught, then we can easily color the vertices by Aleph naught colors. Well, what does coloring number is Aleph naught mean? It means that we have a well-ordering so that from every vertex, only finitely many edges go down. Now, what we do is that we color the vertices via a transfinite recursion along the well-ordering. So what do we have to do at a certain point, where we are at some point? All the smaller vertices are already colored. That vertex is joined into finite many of those smaller and therefore already colored vertices, which excludes finite many colors as the color of that vertex. But fortunately, we have Aleph naught many colors, and then we can find one good color for that vertex, and we can go one step further. So this is the argument in general for any cardinality mu. And Erdős and Hajnal proved that the exact same theorem holds for the coloring number. If the coloring number is uncountable of a graph, that the graph contains C4 or even any circuit of length, of even length, or even any finite complete bipartite graph, or even the complete bipartite graph with arbitrary finite size on one side and Aleph 1 size Aleph 1 on the other side. Well, this coloring number is extremely useful, and it's a very nice property. First of all, it is very close to the chromatic number, as it is visible from this, and it has everything the chromatic number doesn't. One can describe the coloring number in a certain sense by saying that the coloring number is large if and only if a certain substructure appears. One can prove partition theorems. It is possible to know what's happening to the coloring number when we force with some forcing argument. We do some forcing argument. So essentially, it is the tamed version of the chromatic number. For example, one example how better we understand the coloring number is this. What happens if we ask what are the obligatory graphs for being uncountably coloring number, having uncountable coloring number? So we already know that all finite bipartite graphs are obligatory because they must appear in every case if the coloring number is bigger than left not. And we can describe all countable obligatory graphs and actually all obligatory graphs at all. So there is a largest countable obligatory graph and there is a largest obligatory graph. And they are obligatory, they can be described. I'm just lazy to write out the definition here, and nothing which doesn't contain nothing bigger than them is obligatory. And this we don't know for the chromatic number. So if I replace in this theorem coloring number with chromatic number, then we absolutely don't have any theorem like this. We don't even have a conjecture. I have no idea what the right answer would be for the chromatic number. What are those countable graphs which necessarily appear in every uncountably chromatic graph? Perhaps even HUN-REN doesn't know the conjecture. And so what can one do? Well, Erdős could ask very clever questions, one of them being this unsolved problem. Is it true that every graph whose chromatic number is uncountable contains an infinitely connected subgraph? Now, this is a reasonable question because if we replace infinitely connected with a weaker condition, n-connected for any natural number n, then the answer is yes. Well, yeah, K and n, the complete bipartite graph with bipartition classes of size n each must be contained, and as it happens, it is an n-connected graph. So this seems to be reasonable. On the other hand, it doesn't say what obligatory graphs are, what graphs must appear. Of course, if we could the answer to this previous question, then it would be easy because we could just take the list of the obligatory graphs and check if it is true that all of them are infinitely connected. But this conjecture is still unsolved. The other possibility to improve this finite theorem is to ask what finite families of graphs must appear in every graph whose chromatic number is large. Let me give just a very stupid example. There's this theorem that if the chromatic number is bigger than 2, then there must be an odd circuit. Now, do we have something similar that if the chromatic number is bigger than countable, then some finite graph or some families of finite graphs must appear? And to investigate this question, Erdős, Heine, and Szemerédi introduced the following function. Fx, n, is the largest chromatic number of all n-vertex subgraphs of x. So if n is a natural number, I don't know, 26, then we consider all subgraphs of x induced by 26 vertices, consider all the chromatic numbers. These are various numbers up to possibly 26, and consider maximum of them. This is a function from the natural numbers to the natural numbers. And the question is, what do we know of these functions? First of all, fxn is always less than or equal to n. That's trivial. The other thing is that it must converge, it must take arbitrary large values by the Erdős-de theorem. And Erdős, HUN-REN, and Szemerédi found examples where fx goes to infinity as log n or log n or any fixed number of iteration of the log function. And they raised the question if fx can converge to infinity arbitrarily slowly. So slower than all iterated logs or slower than anything. And this was answered. It is consistent. So consistency raised its ugly head. Ugly. That for every function which converges to infinity, f, there is a graph whose chromatic number and size are Aleph1, and fxn is less than or equal to fn. So the answer to Erdős, HUN-REN, and Szemerédi a maybe. At least it is possible. This is a very clever argument which is specific about Aleph1. Another conjecture is the so-called Taylor conjecture. If it is true that if we have a graph X with uncountable chromatic number, then for every cardinal lambda, there is a graph whose chromatic number is greater than lambda, and it has exactly the same finite subgraphs. So is it true that if we have an uncountable chromatic graph, then we can put together from its finite subgraph a graph whose chromatic number is as large as we want? There's reason in this conjecture. First of all, it is true for all examples we understand, we can easily produce. And it is actually true that whenever for all proofs, when we prove that some certain properties may hold with chromatic number bigger than Aleph0, then if we simply replace just one tool in the proof, namely that one which sort of diagonalizes over all colors or whatever, we can simply replace that by lambda many colors, then the argument simply goes through. So this gives in a statement which specifically says that from the chromatic number, uncountable cardinals behave the same. And it is not true. It is consistent, ugly head, that or in one model of set theory, there is a graph with size and chromatic number of 1, so that for every graph y, which has the same finite subgraphs as x, the chromatic number of y is at most Aleph2. And this uses Erdős's Shellow's previous theorem. And also the other consistency result, there is a model of set theory where it is true that whenever x is a graph with chromatic number at least Aleph2, then there are arbitrarily large chromatic graphs with the same finite subgraphs as x. Now notice that these two statements do not contradict each other because of this at most Aleph2 and at least Aleph2 business. So it is quite possible that there is a simple ZFC result, a simple theorem behind this, which says that the Taylor conjecture is true, only we have to replace Aleph1 by Aleph2. If the chromatic number is at least Aleph2, then we can go as high as we want with the chromatic number and keep the same finite subgraphs. Aleph1 is special. Strange phenomena may appear at Aleph1, but otherwise, the Taylor conjecture is true. That's I'd like to see. I cannot resist mentioning one more result. This is about the least chromatic number of a graph, as was already, the definition was already given in Nogallon's talk. The least chromatic number is the same as the chromatic number, except that each vertex has a different set of colors. So the least chromatic number of a graph is at most Aleph naught if the following is true. If we assign all vertices an individual set of cardinality Aleph naught, then we can still color the vertices so that the condition holds. No two vertices joined by an edge have the same color, and each vertex chooses one of the colors of its predetermined set of colors. And generally, the least chromatic number is the least cardinality for which this is true. Now, we have the following chain of inequalities. The chromatic number is at most as large as the least chromatic number, which is at most as large as the coloring number. The first inequality is obvious because in the least chromatic number, we consider some minimum over many cases, and in the chromatic number, we consider the same minimum over less number of cases, so it is easier to attach that. The chromatic number is a special case of the least chromatic number. When to each vertex we assign the same set of colors. And the least chromatic number is less than or equal to the coloring. The least chromatic number is less than or equal to the coloring number. Exactly the same argument works where we prove that the chromatic number is less than or equal to the coloring number. Whenever we are at a certain point, less than mu many colors cannot be used, but we have mu many colors, so one of them can be used. Now, okay, so what is the truth about these inequalities? First of all, the chromatic number and the coloring number are in general different. There are bipartite graphs with large coloring number. The K Aleph 1, the bipartite graph with bipartition classes of size Aleph 1 has a chromatic number, of course, 2. It's bipartite. And the coloring number is Aleph 1, and this holds for any other example. So we have that the chromatic number is less than or equal to the coloring number, but in general, we have strictly less than. So, okay, what can we have? Well, there are a few possibilities. First of all, that we have equality somewhere. Some easy argument shows that one of these less than or equals is in reality equality, or it can be that we may have strict inequality in both cases with some easy examples. And neither happens. There is a model of set theory where the least chromatic number is equal to the chromatic number, at least if we restrict to graphs of size Aleph 1. So if we are only interested in graphs of size Aleph 1, which is the first interesting case, that it may happen that the least chromatic number is equal to the chromatic number, as long as one of them is Aleph 1. And the other consistency result is it may happen that the least chromatic number is always equal to the coloring number, as long as the coloring number is infinite. If it is finite, then of course, they may be different, but that's a finite problem. And this is an application of what we know of the coloring number. If the coloring number is large, then we have a certain substructure which we can handle. And using that substructure with a forcing argument, we can add an assignment of color sets which destroy that the least chromatic number be smaller than that. Okay, now we shift from graphs to hypergraphs. Of course, Erdős asked everything. In the 60s, he asked everything known for graphs if they can be generalized to the hypergraphs. That was a great period of hypergraph theory. For us, a hypergraph is simply a system of finite subsets of any set. So we have a large set of vertices, and we consider some finite subsets of that. If all these sets have exactly 2 elements, then we are back at the graphs. What is the chromatic number of a hypergraph? Well, the definition is exactly the same. The least number of colors needed to color the vertex set so that no monochromatic, no monocolored element of the system is created. So for example, if the system contains singletons, one-element sets, then this is meaningless. There is no chromatic number. So it's reasonable to assume that all of them have at least 2 elements. Now, as in the finite case, everything is infinitely more complicated than for the graphs. Even those small number of things we know for graphs, we know nothing for the hypergraph case. So one step of reduction is that if we restrict for the simplest case, where all hyperedges have exactly 3 elements. And then what Erdős and Hajnal started is a project of doing exactly the same work for triple systems, describe all the obligatory finite triple systems which appear in every uncountably chromatic triple systems. There are theorems. For example, Erdős and Hajnal proved that in the very simplest case, when we have a triple system on an underlying set of cardinality Aleph1, and it does not contain the simplest triple system ever, the one which consists of 2 triplets with 2 common elements, so a triple system consisting of 2 triples on 4 vertices, then the chromatic number is Aleph naught. Okay. And what happened is a big surprise, because it turned out a few years later that this is not true if the condition on being at most a size Aleph1 is lifted. There's something different from the graph case, where if we could prove something for Aleph1 that it went through all the cardinals, Erdős, Hajnal, and Rothschild proved that there is a triple system of cardinality C+, which is uncountable chromatic, and it does not contain 2 triples which intersect in 2 elements. C+ is the successor of continuum. Continuum is the cardinality of the real numbers, set of real numbers. So this is 1 larger than that. So this suggests that the situation is much worse, or at least much more complicated than in the graph case, because we have 1 more parameter, and that parameter is the size of the system. So that may change the answer if we work with different sizes. Now, what happened is that they produced a paper written by Erdős, Galvin, and Hajnal on this topic. Now, look at the page numbers. This paper is full of results, conjectures, examples, and everything, and still there were no final answers in that. And for the main conjectures, some of the, I don't know, more than 12 conjectures are the following. First, describe all finite obligatory triple systems. Do the same job for triple system what was done for graphs. Is it true that if we have two triple systems, S0 and S1, and either can be omitted? So there is a triple system with uncountable chromatic number that omits S0, and there is another one with uncountable chromatic number that omits S1, then there must be a triple system which simultaneously omits both. This is true for the graph case. And the third is this, describe all finite triple systems as for which this strange partition relation holds. In human language, that partition relation means the following. If H is an arbitrary triple system on a set of size LF1, which does not contain an independent set of cardinality LF1, then S must be contained in H. S appears in H. So what happened is that we replaced uncountable chromatic with there is no independent set of size LF1, which obviously very close to uncountable chromatic. Now there are a few theorems on which say general things on obligatory systems. The first is that a finite triple system is obligatory if and only if all its two connected components are how much time do I lose? Negative or positive, just to give the sign. Sorry? Okay. Then, okay, I will just finish. Every obligatory finite triple system is tripartite. Tripartite is the obvious generalization of bipartite, but this does not solve the general problem because the previous example showed that it is not true that all tripartite systems are obligatory. Oops. Let me just mention one theorem and then I vanish. And the one thing, if we consider not only triple system, but finite hypergraphs in general, then it is reasonable to define the coloring number again. Same definition, and the same assumption is that if we know something for the coloring number, then that gives some information on the chromatic number. And there is a theorem which says that a certain, if the coloring number is uncountable, then some finite systems must occur. It's just a very complicated, so that's why I did not include the definition. But this is enough to solve another problem of Erdős. And the problem was the following. Is there a vector space over Q in which there are a set of Aleph2 vectors, which is not the union of countably many linearly independent sets, but every smaller subset is. This was just some variant on some known theorems. Of course, the vector space must have at least Aleph2 elements in order to make this possible, and the answer is yes. And I have to finish now, so let me wish a happy second century to Paul Erdős, and I hope that his theorems and conjectures will live forever.
Thank you very much. Questions, comments? Greg?
So you spoke about fixing the set of finite graphs which embed. I was wondering, what about, what about elementary extensions? Is this also reasonable?
It doesn't seem to be easy to handle. But I'm not the person whom you should ask.
Any other? I have a question. In hypergraph theory, there is also a notion of strong coloring.
Yes, yes.
This makes sense also in the infinite case? I mean,
Strong
coloring being that not only the hyperedge is monochromatic, but all the colors
Yes,
are different.
I think a parallel theory can be built up, yeah.
Any more questions? So let us thank the speaker again. And have a nice lunch break.